We've invited two people from the Space Telescope Science Institute to talk about Hubble Space Telescope data and also some of the outreach issues. Dr. Alberto Conti and also Dr. Carol Christian will be talking, and we'll ask to hold Q&A until after the presentation, please.
Thank you very much, Brian. Let me start with this.
Discovery, go for Hubble release.
The first of NASA's great observatories is now on station at 330 nautical miles above the Earth.
Thank you very much for the ride.
Well, good afternoon. I hope I get your attention. My name is Alberto Conti. This is Carol Christian. We work at the Space Telescope Science Institute, which is the place that controls this beast up here. And what you have just seen in the last 2 minutes are all the press releases for the past 15 years for the Hubble Space Telescope. Hubble is arguably the most successful NASA mission ever. The telescope has changed, really revolutionized astronomy over the past 15 years. And it's part of a series of telescopes that have been built by NASA called the Great Observatories that survey the sky at multiple wavelengths. So Hubble is typically known to serve mainly the visible part of the sky. There was a gamma ray observatory called Compton. There's an X-ray Chandra who is orbiting currently, and there's also the infrared space telescope in Maryland, in Massachusetts, where the headquarters are. And these telescopes basically are revolutionizing the way we do astronomy. So Kara and I today are here to show you how astronomy has been changing over the past few years and where this change is taking us. And we're going to focus on two different aspects. One is the outreach, basically, on what can you do to entertain and excite the public about science. The other issues are what is changing in terms of astronomy. So astronomy went digital about 1960, and ever since, I have to use this, I guess. Okay. I'm scary, yeah. And ever since astronomy went digital, basically, there's been a complete revolution. If you take a look at the green curve here, these are pixels in area and pixels in terms of detectors. So from 1970 to now, we basically gone a factor of 3,000 in pixels, and we have now instruments that basically give us hundreds of gigabytes a night of data in many, many different wavelengths. So the detectors roughly follow Moore's law, which is interesting but a problem for us because we have our data basically doubles every couple of years. So what I'm going to do now, I'm going to turn it to Carol. Carol's going to explain to you how we deal with these massive amounts of data in terms of outreach. And then we're going to focus at the end at how astronomy is changing due to these effects. Carol.
Thanks, Alberto. So I'm going to walk you through some of the imagery and describe the science that we do with the Hubble Space Telescope, but also introduce you to some of the science we do with the other observatories, because both ground-based observatories and space-based observatories work together when we're trying to understand physical phenomena in the universe. So we want to know everything we can possibly know about an object. This is called the Ultra Deep Field. Being from NASA, you know that we use acronyms for everything. So you'll see acronyms throughout some of these slides. This is the Ultra Deep Field. It's the deepest image of the sky that has ever been taken. Pretty much every object that you see here, this part of the sky, which is a very tiny part of the sky, was chosen specifically because in every other telescope it's blank in a short exposure. So just about every object you see here is a galaxy containing, as was one famously said, billions and billions of stars. Our interest in these fields is that we can see what we call relatively nearby, or sort of foreground galaxies that are a huge distance from us, but foreground galaxies, but also the little dots. And if it was darker in the room, you could see. You can get these on the web. Everything's available on the web. So if you're interested in any of these images, have at it. The full resolution images are available. Studying the individual little tiny dots that you see here, these fuzz balls, tells us how galaxies formed in the early part of the universe. And what we've learned is that nearby, quote, nearby galaxies seem to be like, similar to things that are really, really close and like our own galaxies. But the little fuzzy dots are telling us that in the early universe, there were smaller entities that merged and then built up bigger entities rather than just one big thing collapsing and becoming a galaxy. So we're
one plate, or is this a mosaic?
This is it's a mosaic in that to get super resolution, we take shorter exposures with the telescope moving very slightly, and then we build up an image and cut out the best part of it. So there are more data out here, but they're not the same exposure time. But this was done with the advanced camera for surveys, which is 4,000 by 4,000 on a side. And it was one of the largest detectors. Now you can build bigger cameras on the ground and put them on ground-based telescopes, but we have, infrequent access to Hubble, so we can only update the cameras every so on. This shows you a zoom in on some of the objects that are in this field, and it shows you a little better some of the little fuzzy things that I was speaking about that are very irregular in shape and merging way back in the early universe. This is another galaxy. What we're learning about galaxies now is that many galaxies do form out of mergers, and mergers can also occur later in time, closer to our time in the universe, and this is called the Tadpole Galaxy. I find that astronomers are not particularly clever in how we kind of, it comes right out of our mouths off the top of it. Oh, it looks like a tadpole. Okay, it's now called the Tadpole Galaxy. And this structure has been made by the merging of a smaller galaxy that fell into a larger galaxy. And in fact, these kinds of merges, and this image of these two galaxies, these are their telephone numbers, in addition to the coordinates on the sky that we know. This is a really good illustration of how galaxies interact and then spawn all of this stuff. And these are new clusters of stars, hundreds of stars forming together. And in there might be individual stars that may have planetary systems. So if you think back to the UDF, that little tiny place on the sky, which is no bigger than this laser pointer, if I point it into the sky, contains millions of galaxies, and all of them are doing this kind of thing, forming stars. So by looking at the close-up galaxies, we can understand how star formation is spawned by the sometimes by the interaction of galaxies themselves. That object is billions of light years away, so it's taken billions of years for the light to get to us. Closer to home, this is an object actually in our own galaxy, which is a spiral galaxy similar to the ones that you've seen. This is a star in the formation stage. And it's interesting and tantalizing because it has all this material that has collapsed slowly in to make the star in the center, which we can't really see. But the other enticing thing is there is this linear structure, which we believe is a disk. And that's where we believe planetary systems form. So there's a lot of interest in using Hubble Space Telescope to find planetary systems in formation. And we found quite a few that are tantalizing like this, but we haven't actually seen a planet yet because we don't quite have the resolution. But there are other new missions being launched by NASA that will find planets and be able to eventually image them. This is the other end. You saw the birth of a star. This is called the cat's eye. And when I was in 4th grade, I learned that planetary nebula, so-called, because originally Galileo and colleagues thought that they looked like stars with planets around them, actually are very complex nebula. And this is a star very similar to the Sun, but in its death phases. And you can see it has a very complicated structure. So we're trying to understand. We used to think that the star just kind of sloughed off its outer part in a nice, uniform, spherical distribution. But with Hubble, we've learned it's much more complicated process. There seem to be jets, and material spews out and makes these beautiful structures. And there are hundreds of examples of these kind of objects on our website, and every one is different. So it's a real challenge for theoreticians. Here's an example of a cluster of stars that is forming out of the remnants of other stars. So massive stars form, they slough off their outer parts, that stuff gets mixed together, and new star clusters form. And we liked this image because it showed the cluster, but also the beautiful filamentary structure of the gas and dust out of which that cluster formed. Here's an interesting thing that you saw in the movie. This is called a nova. It's another star in its death phases, and remarkably, usually in astronomy, things change over a very slow period of time, but actually, in 2002, this nova blew up and completely changed its structure. So we go back to it periodically and take a snapshot of it. And so we have a kind of a movie of its change. And by looking at the physics of this eruption, we can understand a little bit more about how these stars, what their magnetic fields are, how big they are, what kind of material they have in them, and then what happens to this material later as it recycles into new stars. This is my favorite observation because I proposed it. It's actually this one, Andrew, is a mosaic of many advanced camera for surveys images. It's kind of like, I remember I'm showing my age, my Brownie camera, which I couldn't have taken a mosaic of the Grand Canyon and then suddenly having a digital detector today. This is the kind of advancement we had on Hubble, and this camera was just put up a few years ago. And I cautioned my colleagues to wait for the new camera, and it was really tough to convince them to do that. But we finally did take the mosaic of this galaxy, which is called the Sombrero, and you can see why. So this is the Hubble image of it. This is the infrared image of it, which is completely different. So many of the stars that you saw in the halo, the bright halo, disappear, and the infrared is able to see right into the core of this galaxy and diminishes the effect of the huge dust lane. And then the two were combined in this very striking image. So this is the two great observatories at work together. There are also, of course, this is a radio image. There are X-ray images of this object just to understand what the dust lane is doing, how it's rotating, how big is it, and what is the core of this galaxy doing. We found that in many galaxies there are black holes in the center, and we're trying to understand how big they are and how they form as well. Now this is to show you a comparison of, this is a wide angle image taken from the ground of Orion. So if any of you know any of your constellations, Orion the Hunter, these are his shoulders, his knees, and this is his belt, and he has a dagger. And there's a famous nebula that can be seen by eye, a little fuzzy spot in the dagger. It's been known for a long time. And this is from one of our sister observatories, a ground-based telescope image of the nebula. And then, of course, we always want to image it with Hubble. So this is the Hubble image, and although we can't cover the same footprint on the sky, it does show us some of the detail, and the little movie is just showing the zoom into Orion. So this has tremendous detail now, and we can start to resolve the filamentary structure and start to pick around in here and look for new stars in formation and possibly planetary systems as well. And this just then zooms in and shows finally the high-resolution Hubble image. I'm compelled to show also globular clusters because this is my field of research. Globular clusters are clusters that have millions of stars in them that formed in the early part of the universe. So these are witnesses to the formation of the universe, and by studying them, we can understand what the conditions were like. We have few things around us that are remnants from that time, but our galaxy, the sombrero that you saw, the colliding galaxies that you saw, they all contain these objects. And so we study them because they form together. We learn a lot about stars, how big they are, how small they can get, and how they evolve. And you can also see the beautiful color. The reddish and orangey stars are the big, massive, what are called supergiants, red giants, and the other ones are stars more like the sun. M101 is a classic because the original Hubble images that were taken when we actually had an event that we don't talk about anymore, which is when the mirror was not perfect. This is a classic image that then showed to NASA and the world that Hubble had been fixed, and in fact it had achieved its resolution that we had hoped for. This galaxy is often used as an analogy for our own. So if our galaxy sort of looks like this, we would be about this far out. Our sun is about halfway out in our galaxy, and our galaxy is a pinwheel spiral, very similar to M101. And this just shows, again, that these images have very high resolution. So you can really zoom in with the new camera. You can really zoom in. And in fact, interestingly enough, this little object is actually this object. And you can keep zooming in. And again, these are on the web, so you can play with them yourself. But this is actually a background galaxy that is slightly obscured by M101. But it's way, 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 way more distant than M101 is itself. We also have imaged every planet except for Venus and Mercury because we can't point the telescope too close to the sun because it'll damage the electronics and the mirror, but we've done all the other planets. And in fact, Saturn, we can look at different phases and see how thin the rings are, and also resolve the various ring structures. The ring system of Saturn is actually very complex, made of little rocks of dust, and we're trying to understand why these gaps are here, and it's believed that it has something to do with a resonance with one of the moons. And then this is the famous pillars of creation. It's one of the regions in which stars are forming out of this dark gas and dust, and then new stars begin to emerge. So this is great. You know that we do news, and we put these images out whenever an astronomer has a discovery, and also we have a project called the Hubble Heritage Project. So we find images in the archive, and we go to the person who proposed the observation, say, can we publish your image in color on the web? And they usually agree, and they provide some background information. So that's really the news track. But we collaborate with a number of institutions to get this material not only into the news media, but to provide public information to everyone, to interact with science museums. For example, the Adler Planetarium pulls images online for their shows and also for their cyber gallery. We have a formal curriculum stream where we work with schools and educators to bring astronomy, to develop math and science skills in pre-college students. And then we also have a very robust college education program, because most of our investigators are in colleges and they teach astronomy, and maybe some of you took such a course in your career. The challenge that we're faced with is that we have many, many observatories. We have a whole fleet of observatories in orbit, and we have many ground-based observatories. And scientists, as well as the public, would like to say, tell me about this part of the sky, and get the information. And right now, when you do that, you have to go to each individual observatory to find the information that you want. We have one project of many which aggregate some of this information. There are a number of archive projects that aggregate in wavelength, aggregate in public interest, and we also belong to a project at Space Telescope that is a collaboration across the country with many universities and organizations called the Virtual Observatory. And the idea is to provide a structured layer, and Alberto will tell you a little bit about this, which has data standards and has tools that are standard protocols in astronomy, so that eventually anyone can build an interface and doesn't have to worry about going to each mission or observatory, that through these standards and protocols can get at the data. Right now, this is the science interface to the Virtual Observatory, and it's arduous at best to use. It is very useful for finding out inventory. So I can say, how many observations does M101 have? What have astronomers observed in M101? And I can find out that information, but it's not yet a data aggregator, and we would like to develop a data aggregator so that anyone, including scientists but also the public, can then find and ask a question about the sky and get all the information that's available, because all of this research is funded by NASA and NSF, and the data belongs to you. So at this point, I'll turn over to Alberto, and he'll talk about some of the technical details.
Thank you, Carol. So before I go into a little detail, I would like to tell you actually where all this data that Carol is pointing to basically really is. So for Hubble, for example, the data that Hubble has covered doesn't cover the whole sky. So these are, what you're going to see is a little movie that shows basically where the Hubble data is located at this point. So there's solar system objects. This is the ecliptic, the path of the sun in the sky. There are stars, what Carol showed you, the clusters, the galaxy clusters. But Hubble by no means covers the entire sky. And the reason why it doesn't, it's simple. It's because the field of view of Hubble is much small. It's much smaller than any other telescopes, and also because Hubble does not survey systematically the whole sky. There's a large competition in people that actually try to get time on Hubble. So Hubble really has the time to observe, and usually does observe, the most interesting objects in the sky. But there are other surveys. At the Space Telescope, we host the Digital Sky Survey, which is a survey that covers in 3 different wavelengths the entire sky. Obviously at a much lower resolution than Hubble, but it does cover the entire sky. At Space Telescope also we host many more missions. We host about 15 or so missions. One of them is the Hubble Space Telescope. And some of these missions actually do have full sky coverage. And I'm going to show you one in a second. There are other surveys that are not hosted at the Space Telescope. They're not part of NASA. They're separate surveys. One of them is the Sloan Digital Sky Survey, which in about a few years will actually have covered basically a quarter of the sky, of the whole sky. So it will cover pi, basically, a quarter of the entire sky, to a pretty good depth. And so in 5 different wavebands, so you can generate multiple, if you will, RGB color images out of this. And it's a very, very well understood, well understood and cover survey. But you can see, as you can see, it doesn't cover, for example, it covers only partially part of the southern sky. There's another survey which actually, and by the way, and Sloan was mainly put together because of the interest in studying galaxy evolution. So it mainly surveys galaxies. But there are surveys that are aimed at surveying the sky for stars. So this is the 2MASS survey, which so this image that you see here has probably 500 million stars or something, and all these dots are actually stars. This is the skeleton, so to speak, of our Milky Way in the infrared. So again, this is a whole sky survey. You can point in any direction in the sky, you're going to find images from the 2MASS, from this infrared survey. So as you can see, we have multiple coverage across the whole sky from multiple surveys. Another interesting survey, which is not complete but is starting to be complete, which is also hosted at the Space Telescope Science Institute, where Carol and I work, is GALEX, which is an ultraviolet satellite, which will have a whole sky survey. And this galaxy, I don't know if you remember this, but Carol just showed you this. This is M101 again. I just realized this morning, actually. And so this is actually the view of that galaxy that Carol showed you in the infrared at resolution, in the ultraviolet, at a resolution that was not even thinkable just a few years ago. So, and again, in maybe a couple of years, there will be a UV image, ultraviolet image of all the sources in the sky up to this resolution. And just to give you an idea of the scale, this is about 3,800 pixels on the side. So where does one go if one wants to get all this data? So in the United States, and particularly NASA, there are lots of data centers. The data center in blue here is a data center that hosts visible and ultraviolet data at Space Telescope, where Carol and I work. But there are other data centers, namely there's data centers that have high energy astrophysics, meaning X-ray data. There's infrared archives, URSA. There are archives that hold microwave background data, so it's very different wavelengths. And then there are archives, for example, like ADS, which hold really all the publications that astronomers make and publish links to these data archives on where you can actually go and get the data. And then there are other databases available to astronomers, which actually they're like yellow pages, so to speak. You can go to NED for the extragalactic database, and you can basically, what you can do at this NASA center, you can actually ask, I want you to search for M31 or for Andromeda, and this will do a name resolving, so to speak, for you, and it will give you the coordinates on the sky and point you to all other observations that are available about these objects in the other data centers. So astronomy, as I said at the beginning, has come a long way. In the past few years, we have been entering basically this new era of astronomy, which is the era of large surveys, and now many of them are coming to be multi-terabyte in size. The Sloan Digital Sky Survey, for example, has already many more than 100 million objects, and by objects I mean galaxies and stars and anything else. And there are other surveys that are being planned, and so at this rate, we're really going to have a problem actually even publishing data, making the data available to the public, not because the data volume is so large, but also because it's going to be hard to have people find the data in a meaningful way. On top of this, as I just showed you, there are going to be many more all-sky surveys and in many different wavebands. And so multi-wavelength, basically, astronomy is starting at a frantic pace, I should say. And so this will just make the problem even worse. And the good news is that there have been already impressive discoveries just made by using for all the people that have access to these hundreds of millions of objects. There've been some impressive discoveries already made. So we're going in the right direction as far as science, but we still have problems. So what is the problem really? So we have, if you count all the data that we probably have a few petabytes of data, which are basically online somewhere, somehow, in data centers in Europe, in data centers in the United States, across the world, basically. But the problem is that with this data, we have, we're interested in basically in getting some science out of this data, mining for interesting objects or weird objects that we have seen or new classes of objects. And the problem is that each of these objects that we are basically tagged with a property, like position you can think of, like some brightness or some color, some type, if there's a galaxy, a star, or some size, depending on how close to you they are, or if they're intrinsically small, for example. So we typically are dealing with multi-petabytes data sets with objects that live in this 400, let's say, dimensional space. And so this is not easy. So it's not easy to deal with. On top of this, as I said at the beginning, the data basically doubles every couple of years due to the growth in technology and detectors. And so the publishing of the data is really one of the key problems that we're encountering at the moment. And on top of that, we really lack, and I'll show you why in a minute, we really lack good visualization and query tools for this amount, with these amounts of data. So astronomers were used to just concentrating on just a few objects that they can study them at length. Now they can actually study at length millions of objects, but they don't have the tools to do so. One of the answers to this question is an alliance. It's an international alliance that has been formed a few years ago, and is trying to federate basically databases across the world that have astronomical data. It's called the International Virtual Observatory Alliance, something that Kara alluded to before. And the U.S. partner in this alliance is called the National Virtual Observatory, which is, again, the project manager for that is actually a Space Telescope, where Kara and I work. But there are, as you can see, there are collaborations across the world, basically. And the idea is that we should be able to come up with some sort of standards built on top of what astronomers already know to actually be able to talk to each other and try to make sense of this large amount of data that we have really at our disposal. And historically, astronomers have been pretty good at actually establishing standards for their data. One of the cornerstones of their standards is the flexible image transport system, this FITS file, which is a standard in astronomy. It's like an HDF file basically for GIS. So just to give you an idea what it is, it's a system that it's a file type that allows you to carry information. It has a header. And the header is very useful because you can see a little example here. It shows you, basically allows you to understand what kind of coordinate system you are in, what kind of projection you're using for that particular data, how you can, let's say, rotate this data or deproject this data and reproject it. So it allows you, it gives you some metadata about the data you're carrying. It has a very simple scheme. There's a keyword value statement in the header. And the interesting thing is that, and this was built, I think almost, the idea came up almost 30 years ago, actually. It was supposed to contain both digital images, which is the pretty images that we showed you, but on top of that, it's supposed to contain also catalogs that basically address the fact that, okay, I have this pretty image, now tell me which ones are the stars, which ones are the galaxies, for example. And it's pretty intense in the sense that you can have tables, if you will, in there. So you can have multidimensional tables inside a structure of this type.
I'm supposed to remind you that FITS is as old as 8-track tapes. It was invented at about the same time. So astronomers kind of got our act together early, which is a good thing.
Thank you. That's right. I forgot. But we're also aware that things are changing around us. So we have to take a look at more flexible ways of really not using FITS, because FITS is mostly for the data, but really thinking about how we can describe the data. Think about the metadata. So the Virtual Observatory Alliance came up with a particular XML schema, if you will, to describe astronomical data. It's called a VO table. There's no transport of information in here other than, imaging. It's a pure means of or of talking either between computers or humans, if you can read this, of describing basic resources that are available to you in astronomy. And it's mainly used to carry information about catalogs, about list of images and where they are located, and other resources. Let's say I want to know where this particular observation was made and when it was made. I can actually query some service that will return this to me. And I'll show you in a second what I mean. And the other cornerstone of our standards is a world coordinate system. So we understand very well several kinds of coordinate system, from galactic to ecliptic to different epochs in equatorial coordinates, and we are very, very good at understanding all of this little jargon here, what all these projections really mean. So these are just some of the projections that are used in astronomy. So TAN is the tangential projection is extremely popular, but nevertheless we know this is pure math really, so it's not too hard, but we know how to transform from one to the other. And then recently, this is not a standard yet, but it's something that has come to the attention of the entire astronomical community, and it's the fact that, to some extent, having all this data online is great, but at some point we need to be able to find it and find it quickly. And so I call this the zip code in the sky. It's a way to basically to index the entire sphere, the entire sphere, for you to be able to ask very quickly, find this object and find me all the neighbors that it contains in less than a millisecond. And I'm querying billions of objects. So this hierarchical triangular mesh index is basically it's a 64-bit integers that allows you to find objects at different resolutions very, very quickly. It's been implemented in databases and right now lives as a stored procedure in Microsoft SQL Server, but is a very efficient and at allowing astronomers to find in very large databases basically a particular point in the sky. And so around this and around some of the standards that I just showed you, the VO, the National Virtual Observatory in the US, but also across the world, the Virtual Observatory Alliance, has developed some simple services. These are all web services because we recognize that at some point there are going to be lots of machines talking to each other. So these are all sub web services. And one of them is a very simple one. I want you to give me all the objects around this particular region. And this is as trivial as asking a database basically to return to you the list of objects that it stores. But then there are other standards, and one of them is obviously an image access protocol. So you can actually ask a server to give you basically an image or a location for that particular image. And then again, they're based on fits and their returns as this particular XML standard that we're using. And then there are other sophisticated, I'm not going to go into detail, but there are more sophisticated ways to query databases across the entire virtual observatory that allow you to ask a particular database for some objects, to ask another database for the same objects, and then to put them together and find and figure out which one are the same objects or not. It might seem a trivial task, but it's really not, because many databases have different resolutions across the sky. And then, just to show you what kind of interface astronomers are used to right now, this is a mission again hosted at the Space Telescope Science Institute, and this is a typical form that astronomers fill to find their data. It's almost primitive, I would call it, but it's a very simple form where you actually say, I want Andromeda here, and then the coordinates are populated, and then it's going to return to you some information. It's going to return to you the position in the sky, magnitude, which is brightness, some measure of how much dust there is, maybe. And these are typically what we have. But the astronomical community has been growing a little bit more. The growth of the astronomical community has been a little bit more interesting. So lately, they've been asking for interfaces that actually do a little bit more, that allow you basically, we expose to the astronomical community the entire database, and we allow them to call SQL straight SQL against a database and ask for any questions, so to speak, that they want to answer, which is something that they cannot do with the form, which is with the previous form that I just showed you. And then finally, there are also this is from the Sloan Digital Sky Survey. There are also interfaces that go beyond that. They don't return to you a list of objects. They want to return to you images, basically. So this is what's called the navigator on the Sloan Digital Sky Survey. It's a very interesting interface. It looks almost like a MapQuest or Google Maps. It allows you to navigate the sky, and it allows you also to click on individual objects. And for each of these objects, you can have information such as obviously position, but also such as how bright they are. And this is interesting because the emergence of these tools, of these navigators, is actually something that is actually needed in astronomy in general. And the interesting thing is that there are a series of web services that plug into this interface where you can actually find, for example, all the objects that are being detected in this particular field, or all the objects that have a spectrum, or all the objects that are detected in a particular field in this area. And they allow you obviously to zoom in and out. So let me conclude here. I think what we want like for you to go home with is really that there are this many square degrees in the sky. These degrees in the sky correspond to basically 2 trillion pixels or so. At one wavelength, astronomers have to deal with 4 terabytes. This is what the entire sky is. Not a very high resolution, I might add. But there are multi-wavelength surveys that are coming online, and so this is the volume we're going to look at. Maybe hundreds of terabytes or so for multi-wavelength surveys. And then something I never even touched on is if you add now the time dimension, which means suppose I want to find objects that have varied since my last observation, this number might actually go up by a large factor because you have to survey the sky repeatedly. And there are telescopes that are coming online that are going to survey the entire sky every 3 days. And so this is the volume that we expect. So the challenges that we're facing are all this data is really hard to publish. And not only the programs that mine the data are hard to publish, but the data in general is hard to publish. It's hard to find and understand the data because there's a massive amount of information and the interface is actually not well developed. So what we need is a new paradigm, basically. We need to look at the data in a different way. We need to look at analysis tools and visualization tools in a completely different way. We need to think about it sort of out of the box. And at the same time, we have to realize that we have to do some education within the community because there are sociological issues here involved. You know, when astronomers don't concentrate anymore on just a few objects, they need to think about hundreds or millions of objects. There's an issue here, which is maybe as simple as educating astronomers and having them learn SQL or just exposing them to new kind of technologies. So I'll stop here, and if you have any questions, that's Carol's email for all the complaints, and that's my email for everything else. Thank you. Any questions? We should kill them all. Please.
Yes, but it's on the HTM format. Just trying to understand the point. If the purpose is to make it easy to say find stuff near this point, what's wrong with just saying, you know, degree range vertical this, degree range horizontal that? Done.
Right. So you could do it that way, right? So you could do it that way. Yeah. The question is, why do you use the HTM index as opposed to just doing a straight positional cut, basically, in the sky? So you could do that, right? It turns out that HTM is extremely efficient at answering that question that you just asked. There are issues related with the fact that we are cutting in position in the sky on a sphere. So it's not that as trivial as it seems. And it might be that you are projecting the data in a particular projection system, so you have to do additional calculations. HTM is very powerful because it's hierarchical. So I can actually concentrate on just a particular edge of the sky and then drill down to the resolution I want. And it's very, very fast. So we're talking about a factor of 100, maybe 1,000 faster than doing what you advocate. Any other questions? Brian.
Projections and lat long versus other kinds of data. What is the typical storage format, and can you project it all into one space, kind of like we do with Earth?
Yeah. So the question is, we use lots of projections, and is there a single projection system that we can actually possibly use? The answer is yes. I mean, in principle, the most common one is a tangential projection. Right. Not everybody does that, but it is actually not hard to project or to reproject, as you will. There's the issue only since you consider a sphere at the poles. So you have to very, very pay, as you probably well know, for Google Earth. There's the issue at the poles, right? But I think there's nothing. It really depends. So the way I was thinking about this is like if we had a tool that actually would browse the sky, at some point you might want to, as you approach the poles, you might want to use a different projection. Right, and so that might be, it's probably better. But in general, yes, the answer is yes. You can, with a little bit of work, you can project astronomical images onto let's say, a tangential projection. Carol.
I was also going to mention we have a similar search problem, if you will, if I can make an analogy. The sky surveys are like Landsat, right? It's time ordered, essentially, and that's how the sky surveys are done. And lots of times the archives are built that way, so that's time ordered. But the pointed observations, like the digital globe or the Iconos, QuickBird, all that stuff, that's pointed observations. And we have pointed observations too. So we have to marry the two. When you do a search, you have to search into archives that are time ordered and position ordered. So that can be tricky as well.
Yeah, that's right. And so adding on that, I didn't even mention the time domain, but the time domain will give us even more headaches than we can even think of, because is a really non-trivial problem. When you keep observing the same part of the sky, and how do you find objects that vary from the previous observation or something? So it's something that that has been on the minds of astronomers for a long time. Wait, you first, and then go ahead.
Why are the radio images such a low resolution compared to the well, not just the Hubble images, but any visible spectrum images?
Okay, so the question is, why are radio images such a low resolution compared to visible? As actually, you want to take this? It's actually easy.
Well, radio waves are very big, so you need a very big antenna. So a typical radio dish has to be the size of this room to even get a modest resolution. But you know you have a digital camera with a small lens that big, and you can get quite exquisite visible images. And it's because of the nature of light and nature of radiation that visible light is really tiny, and so you can resolve it with a tiny lens or mirror, whereas a radio wave is very large, and to collect many of them and bring them into focus requires a large facility. So, for example, Arecibo in Puerto Rico is a very large dish. It has an interesting resolution, but now what radio astronomers build are called interferometers, where they, instead of building one big dish, they simulate it by having many dishes and then combining it. And then you can get to the higher resolution. If you have, like in Arizona or New Mexico, there are, fields of little radio dishes, and then you combine all the signals together, and then you can get the same resolution. But it's the nature of light, that radiation. The X-ray is really, really, really tiny, so you can get really high resolution, and then visible, infrared, and radio. And so your detector has to be the multiples of the wavelength of the light radiation that you're trying to detect.
Did you have a question, Brian? Sorry, Brian. And
So talking about compression and time, I mean, it seems like since very little changes over time, that you can get huge compression winds by just doing delta compression. And so hopefully you won't end up with petabytes of data.
maybe, yeah. Maybe. So the question is, you might not end up with petabytes of data if you actually use high level compression, basically, too.
And that is what LSST.
Yeah, so LSST, which is this new survey telescope, which will basically survey the sky every 3 days, the full sky. And we'll actually try to do exactly that, because they're looking for asteroids, right? So the idea is, okay, asteroids move very fast across the sky, so I'm looking for things that are changing, moving from one place to another overnight. And so the idea is that I can store, I don't need the highest resolution images. I just need to compute the difference between images, basically, very, very efficiently to find them, yeah, so. Are there standards for the image compressions? For lossless. Yeah, so FITS is an image compressor. So it does some compression. It's not extremely efficient in compressing because it was built a long time ago, but it's quite effective at compressing. So yes. Andrew?
The false color images are very beautiful, but what I'm not sure about is how completely automatable the false coloring is to make it so nice. And I'm wondering, to what extent do you have artists special casing those pictures, or is it something that we can pretty much automate so the public can always see beautiful false color?
I think that would be an interesting project. To get the highest quality for the press releases, we have one person who knows how to do this, and he is an artist. He's a scientist as well, but he is an artist, and he's been mentoring other people in the process. So it's possible to do a quick and dirty color image and do combination. You do the registering, and then you decide a color balance. So we could do that if you wanted the highest quality stuff. That's why we don't actually produce everything in color. It's because we produce the best of the best, and it does take some time. But I think you can get sort of a baseline color image, and in fact, Sloan has done that.
Yeah, so again, I was going to say exactly that. So Sloan has done this systematically, right? And again, the navigator in Sloan is an example, right? So it might not be the best, let's see if I can bring it up. It might not be the best looking galaxy scientifically speaking, but it's actually pretty good, right? And so they've done this systematically, very quickly, trying to match, blue is very hot here, and this is, probably older population of stars in this particular galaxy. This is a fairly young galaxy. So they try to keep the science underneath it, right? But they've done a pretty quick and dirty, and it works pretty well. So I think the answer is yes.
I was also going to add, with the sky survey, you have a set exposure time, and so how each filter is going to be exposed for a certain amount of time, and then you can automate it. With Hubble, it's up to an individual to specify the observation. So what Alberto wants to do with his data and what I want to do with mine are very different. So our pointed observations are different, and they take a little more tooling. But in fact, the scientific community is starting to exhibit a little impatience with having to do all the process themselves. So we're starting to look at automated processes for scientists as well. So.
And he also, I guess, just to add to this, it really depends on the audience, right? So if you're really talking to do this for outreach purposes, and you want to develop a navigator which has the first thing you want to do is not really carry the scientific information. You want to maintain some scientific information. So you maybe care a little bit less about being accurate 100%, right? On the other hand, if you really want to serve the scientist might even actually not care about the color image at all. He might want just a straight image from the telescopes, right, and then do whatever he or she wants on their own. So yeah.
Do you have other junk in the way when you're to deep space? I mean, by junk, it could either be a satellite or it could be an asteroid or rock or planet, whatever it is.
That's interesting. What junk? So Hubble. Yeah, the question is how often does Hubble see junk in the way, basically, of our observation, right? That's a very interesting question. I wish I had an image here, but I don't have it, right? Of how the data actually gets to us, to Space Telescope from Hubble directly, right? So, we showed you very, very beautiful pictures of the actual images, but in reality, there's a lot of junk that you actually don't see and has to be cleaned, right? So there's space, to make an image like this. If you take a look at this image when it comes down from the telescope, it's extremely, extremely different. And okay, the junk I'm thinking of is not the junk you're thinking of, I think, right? So you do see sometimes trails of asteroids, right? Extremely rare because the field of view of Hubble is very small. So the probability of intersecting something is very tiny, but you do see sometimes. But what you don't see here is that the images need to be cleaned because there are particles, high energy particles in space called cosmic rays that hit the detector constantly. So they need to be cleaned, and they cause trails which are similar to asteroids. So if you see a non-clean image of Hubble, it's going to be full of these little trails. And so that's why Carol was saying at the beginning that they move the telescope around, because each pixel then is hit by a different set of these, right? And then you can clean them up later. It's called a dithering pattern. So they have a pattern that maximizes the resolution of the spacecraft. So, and I'm trying to think about other satellites, but I don't know if actually Hubble has. There were other satellites, because Hubble is 300 and some miles away.
Right. Most of the satellites that we were speaking of are in low Earth orbit, and so they're all within a band around the Earth, and so they don't really very often pass over each other. But one of the other hazards is when we go through the meteor shower. So we have this big frantic thing when we go through the meteor shower and we close the mirror. And a little anecdotal story is that we had a prediction 2 years ago of when the meteor shower was. It was a Perseids, I think, which is in August. So we're all ready, we're going to turn the telescope away so that its butt end was into the meteor shower, right? And we closed the mirror and everything, and the prediction was off by 15 hours, and it sat pointed straight into the meteor shower. And then we turned it and closed everything down and found out later that we had completely missed it, but the telescope wasn't damaged. So we have problems like that. But pretty much the satellites don't pass over each other because the orbits are really very carefully monitored.
But there's a lot of junk, right? But it's not that much. So the question is, how do you access the data, basically, right? What do you do? So for Hubble data, we used to actually make DVDs and send them to people, right? But now DVDs are too small, right? So 5 gigabytes is nothing, right? So you have lots of, and so right now the preferred method is actually, they'll allow you to download it from the web. There are sites, if you go to the Space Telescope site where we work, there's an archive link, so you can actually go and download the link. But even that is becoming a little bit problematic now, because some people would like to have the entire Sloan Digital Sky Survey, which is 2 terabytes. But over FTP or over anything, it's pretty silly. So what we're trying to do is we have the problem, right? We have the problem people asking a lot of data. So what we try to do is that many of them ask a lot of data because they don't know how to search for less data. So what we're trying to do is try to build interfaces for them to cut down on that data and say, I want just this particular observation, even if it's 5,000 objects or a few gigabyte. Then that's what you do. Yes, Carol.
This is an example of the VO interface. Alberto showed you some other interfaces, but right here is here's an option. You can save it locally. So you select all the stuff you want. So this particular observation was for a globular cluster called NGC 6624, and it turns out there's some deep sky, digital sky survey images, there's some HST images, there's some infrared images, and then I can click on here and then save the whole thing locally and analyze locally, or I can analyze online with a tool called Aladdin. So typically what people will do is they will select their data, actually download it to their desktop, and then analyze there.
What kinds of interesting things have people done with downloaded data?
Scientifically or publicly?
Scientifically.
Okay, so the question is what have people done, with the data they've downloaded. I don't know. Scientifically, I can go on for a while here. There are lots of things that the people have done. There are people that have discovered new objects, right? New classes of objects that were not there. There are people that have discovered that old objects look very different now if you compare, like Carol showed, multiple wavelengths, right? You see, for example, the Alberto Galaxy, you see some image in the visible and a very different image in the infrared, and this tells you what's going on in that galaxy. So people are doing a lot of work on this. I don't know if you want to add on something.
I was going to say for Hubble and for the most of the observatories, an individual scientist can specify an observation, like we specified the sombrero, for example, and then to study the dust lane in that galaxy. But then the data became public. So the power of the archive is another group. I just went to a conference a month ago where another group looked for clusters in that galaxy. So different groups look for different things. They want to study different things with the same data. So our philosophy has always been with the archives. The archives are open after the originator of the observation has some period of time to analyze the data. Then the archive's open, and anybody can get in there and take the data and do whatever kind of research they want. And so that really is starting to pay off.
Okay, thank you so much. Thank you.